Are you tired of buying different batteries for every project? What if you could have all of your common voltages from one rather simple circuit? So far in our Electronics Learning Lab series, you can see up until this point, we have used a voltage divider, and this has worked for demonstrating things like how a switch functions. In my last video, however, you can see this was no longer the case as issues began to rise. A voltage divider is unregulated. You see, we simply divided a voltage into equal portions to simulate battery voltage values: 1.5, 3, 4.5, 6, 7.5, and 9 volts. Once we began putting a load to part of this divided voltage, things began to become unbalanced, uneven, and, well, it just kind of showed that it was unregulated. In this video, we will be covering how to build a multi-voltage, adjustable, regulated power supply using the LM317. A voltage regulator is an electrical device that maintains a constant output voltage regardless of changes in input voltage or load conditions. Some popular regulators are the L7805 and L7809, which are a positive 5 volt regulator and a positive 9 volt regulator, respectively. What makes the LM317 so special is that it is adjustable anywhere from approximately 1.25 to 37 volts. The LM317 has 3 pins. Pin 1 is for the adjustment, pin 2 is the output voltage, and pin 3 is the input voltage. We will circle back to this, but know that pin 2 or V out is connected to the regulator's back plane. The LM317 includes current limiting and thermal overload protection. According to the datasheet, typically no capacitors are needed unless the device is situated more than 6 inches from the input filter capacitors, and this is my case, so I will be using C1 as an input bypass. In the basic datasheet schematic, it shows C2 can improve transient response, and I didn't think I would need it, but as you'll see later in the video, I did need a capacitor in my output, but we'll get there later in the video. The circuit has 2 resistors, one of which is variable, which is what makes the voltage adjustable. The circuit shows using a 240 ohm for R1 and a 5K potentiometer for R2 with a 24 volt input source. So what should our source be? What outputs can we create? How do we calculate this? Glad you asked. Let's get into it. In the datasheet, you see this portion that shows adjustment current times R2. Well, good news. The adjustment current is typically 50 to 100 microamps, which is a very small number. So small, in fact, that it can be ignored for our situation. And with such a small value, any R2 value multiplied by it, this portion of the equation can just be ignored. This leaves us with the formula V out equals 1.25 times 1 plus R2 over R1. Another worthy note to take from this data sheet is the input to output voltage, or VN minus V out. This must be a minimum of 3 volts. Therefore, I want a regulated 9-volt maximum, so that is why I chose a 12-volt source to have that 3-volt difference. Some refer to this as headroom. So let me walk you through this. If we wanted 7.5 volts out and our R1 is 220 ohms like I have, then we'll be looking at something like this. Okay. So first thing I'm going to do is I multiplied everything by 100 to get rid of our decimals. Then I'm going to divide each side by 125 so I can just get rid of these parentheses over here. So that will give me 700 over 125 equals to what was in our parentheses. Then 750 over 125 is 6. Now we're going to want to remove this 1 from each side, so subtract 1 from each side. We're going to get 5 equals R2 over 220. And now we're going to want to multiply each side by 220 to get rid of this fraction and isolate R2. So now we have 220 times 5 equals R2, and 220 times 5 is 1100. So for 7.5 volts out, using 220 ohms for R1, R2 will equal 1.1K. And now quickly I'm going to solve for the other 5 so I can set my pots to them. Now remember, even though I have 6 output voltages, doesn't mean you have to also have 6. You can have 3, you can have 7, however many you want. My goal is to replicate the Learning Lab electronics kit from Radioshack. In theory, you could follow this equation, find your resistor value, and have a actual resistor, not potentiometer, and just have a fixed value if you wanted to. Okay, so here I have my simulation, and on the left side of the datasheet, there's a lot to go over real quick, I guess. Let's see. So I have here all 6 of my chips. You're going to want to use one LM317 per, V out that you want, essentially. And I want 6. Here's the schematic that I'm going off of. Here's where it says, if it's more than 6 inches away, you see 1, which I do. So here's 0.1 microfarad. That's where you see this. And I'm going to go over C2. Typically, you don't need this, but I did need it only on my U1 that I'll talk about in a second. But that's why I only have the 10 microfarad on U1 because that's the only one I needed it on. Everything else is pretty much copy and paste. R1, instead of 240, I had 220 half-watt resistors, so that's why I'm using those. And then, as you remember, this is a fixed value resistor, but I will use potentiometers instead. But this is just to run off my calculation. Remember, we got 1.1K for 7.5 volts, so that's this right here. My circuit is turned off right now. Ignore this portion. This is for later. But let's see here. What else do I need to talk about? Yeah, so R2. It's a variable, but, that's what these are. I just calculated it. And instead of putting a variable in my simulation, I just did a fixed value of the calculated value. This line voltage, that's my VN, my 12 volts. Common is my adjustment pin, and V out is my regulated voltage. So I guess let's hit play. Let's run it. So as you can see here, I'm getting on my U1 chip, I'm getting my voltage. My 1.5 on this output, my 3 on this output, 4.5, 6, 7.5, and 9. Pretty close, you know. Overall, this circuit uses about 34.4 milliamps. And if we check real quick, um, 34.4 milliamps times our voltage, 12 volts. So we should be using about 413 milliwatts. Oh, I guess I could, let's see, probe it. Yeah, as you can see, we're using 413 milliwatts of power in total. So the bigger the difference between V in and V out, the more power you're going to have dissipated, right? So 9 volts is closer to 12 volts than 1.5 volts, right? So as you can see here on this one, I'm only using about 17 milliwatts, and the more difference there is in voltage, the higher the wattage, the higher the power is going to be. And if you add all these up, you'll get a total of 413 milliwatts. Okay. Let's see. So right here, I'm gonna explain this real quick. So I was getting like a kind of faulty value of my 1.5 in practical on the actual circuit board. It wasn't very stable, and that's before I added the 10 microfarad. As soon as I added this, it became stable, and my 1.5 was constant. It was kind of switching between 1.5 and 3 volts, but as soon as I put this in there, that went away. So that is why I put this in here, and so far I've only needed it for U1. And then I also, if you see, I have a diode right here. The reason why I put that there is because it shows here if protection diode D1 is recommended, D1, if CO is used, which I did for stability purposes. The diode provides a low impedance discharge path to prevent the capacitor from discharging into the output of the regulator. So that is why I have a D1. You'll notice they used a 4002, I used a 4001. The difference being this is rated for 100 volts, mine is rated for 50 volts. This is plenty okay for what I'm using it for. And yeah. Real quick, I just want to say that my input, this like what's plugged in my wall, coming out of my wall, is a 12 volt maximum 1 amp source. This chip can handle up to 1.5 amps output, I believe it says. Max 1.5 amps. So I definitely don't want to push this thing to its max and for what I need it for. And I'm using it on a breadboard, right? So, you know, on breadboard, I don't want a crazy amount of current. You know, I'm not going to be using very much current, showing all you guys this. But as you saw in my last video, you know, this was dropping down. This is the same circuit from my last video. And you saw the voltage go down to like, whatever, 2.3 volts with the voltage divider. So now, let me connect it. Let me get this out of the way now. I'm going to connect it so this is all the same values. I can't see. So the buzzer is connected to 9 volts and the LED is connected to 3 volts. And this dropped down to like 2 point something volts. And now this time, watch this. As soon as I close the switch, LED turns on, buzzer's going off, and look at that, constant 3 volts, 3 volts. It's regulated. This is what we wanted to see happen. Awesome, right? So if you want, only 3 of these, hey, just use 3. If you want 4, just use 4. As you can see, they're pretty much copy and paste. Other than this one, I needed the output capacitor and the diode, but I didn't know that until I got to the hardware application and I saw that it was kind of fluctuating. So, what are you doing up here? Delete. Okay, so now, I know, exciting simulation portion is over. Let's go ahead and check out, let's build the circuit hardware-wise, and then we'll check it out and do some adjustments and see what it looks like. Alright, really quick, I'm going to show you how to assemble one of these onto a heatsink if you choose to use one. I would recommend it just because they can get a little hot, especially depending on your circumstance. So we got a screw, some insulators. Here's all of our pieces. First thing I did is I ripped this pin off because I'm not putting it into a PCB. I'm using a breadboard, and with this on there, it can almost short your pin 2, your V out. I'll show you that later. But so first thing I would suggest doing is, if you're using this on a breadboard, is to just rip this pin off. Okay, so you got your heat sink ready. First thing I need to show you. Sorry, jumping ahead. Need our meter. Okay. Pin 2. Your output voltage is connected to the back plane. If you see, we have a short. Okay. So your middle pin, pin 2, is connected there. That's important to note for later. Okay. So let's take this. Now we're going to take our pad. The purpose of this pad is to not let the back plane of this guy touch or short to the heatsink. Okay, we got this like Lego stud looking piece. It's hollow. You see one is like skinny side. We're gonna take the skinny side and put it into the back plane like that. And now our screw. So now what this does is our screw will not touch that back plane. It won't short it because this screw will be connected to the heatsink. So right now nothing should be shorted. The backplane should only be shorted to pin 2. So I like to screw it on until it gets snug, but then I can still move it, you know? And I like to get it nice and straight. And then with one finger, just hold it down in place, and then you can tighten it down. Okay, now it's good and tight and straight. Now you can bring in our meter again. Okay. And again, pin 2 to our, try not to, pin 2 to our V, to the backplane should be a short, as shown. Now if I were to touch the screw, that should be an open. We do not want that to be connected. Same thing with the heatsink. Not connected. That is what we want. Now the screw will be connected to the heatsink. Okay? But we don't want our output voltage to be shorted to the heatsink. So just a couple checks to do. This one looks good, and that's how you do that. Okay, let's start building the circuit now. So I already have all my grounds on my boards. The first thing we're going to do is be bringing in our power, which remember will be pin 3 on each LM317. And then I'm going to, and I have 6 of them. The yellow wire is just bridging it over. Next, I'm going to make a bridge for pin 1, the adjustment pin. So blue pin 1, yellow pin 3. Okay, now I'm going to be putting in my R1 value, my 220 ohm half watt resistor. That's going in from pin 2, crossing over to the other side of pin 1. And now I'm installing my C1, or my bypass capacitor, 0.1 microfarad. Okay, next is my output, or sorry, like my wiper to ground for each potentiometer. Now I'm installing each one of my pots. I've already tweaked them to the values calculated from earlier. And now I'm just bringing over the connection between R1 into the pot. And now here's my V out value. I'm just bringing that down on the board so I have another place to tap off of. There will be pictures at the end of this giving you other views as well. Okay, now I can go ahead and start throwing in my LM317s with the heat sinks attached. Here's some additional pictures, give you different viewpoints. And also upcoming, you'll see where I installed the 10 microfarad output capacitor across U1 and the diode for U1. Oh, see, here's I'm bringing the V outs to the proper rails that I want. There's the output cap for U1 and the protection diode. Alright, so now that we're here, we got the output capacitor installed and the protection diode. Ignore this for now. This is the circuit from the last video that wasn't working properly. I got it all set up on the new one. We'll go over this in a second. Got my 12 volts plugged in. So my power switch is off. I am on my 1.5 volt rail right now with my multimeter probes. And so if I turn this on, okay, my 1.5 volts. And then now if I want to adjust it, I can just tweak this. And if I wanted to, I could bring this to 3 volts or 2 volts if I wanted to. Okay, so my 1.5, that's good enough for me. 3 volts, I could tweak this, but this is okay. Four and a half. Let's meet this one. We're good there. 6. Right on the money. 7.5. I could tweak this one. And my 9. Cool. Perfect. Turn that off. There we go. Okay, so now let's go ahead and redo this that we did with the voltage divider. Now that everything's plugged in, calibrated to where we want it, let's see what happens. So, let's see. The buzzer got 9 volts. And the LED should be getting 3. Okay. I'm gonna not leave this on for too long because the buzzer is super annoying and we just want to see it work. So, I guess I just want to probe right here to make sure that I'm getting a consistent solid 3 volts DC. So, okay, I'm gonna plug this in, turn it on, okay, and flip this on, power's on real quick. I already have my solid 3 volts and we should not see a change in this after the load is applied. There we go. Lights on, buzzer's going, and we still have our very consistent, regulated 3 volts. And yeah, whatever, we can do 1.5 volts if we wanted to. 1.5, let's see what happens. It's just much more dim. Let's bring it up to 4.5. So now you'll see it be brighter. 4.5, perfect. Turn this off. Cool, looks like it works. So I got a whole bunch of these off Amazon. These little voltage meters that you see. I'll show a video right now. They are kind of garbage. Really thin wires. so thin that I ripped it off and I just made my own. Kind of like that. I left the yellow wire. And then when I did this power off. This allowed me to just plug it right into the rail like this. And then I could put this yellow wire. So you want your red and your black to have, I just used the 12 volt source for it. And that worked. And then your yellow wire will be whatever you want to measure. So I could have measured right here, or you can put it on each rail that you have your voltage, so you can measure all that. And then there's like an adjustment screw on the back. So if you wanted to match it with your meter, you can calibrate it. But it's pretty close. So I mean, they're really cheap. They're on Amazon. Don't expect much of them. They look cool, but yeah, they're kind of garbage. One thing I will tell you is don't try to power this. You can like tie the yellow and the red together if you are measuring the same thing, right? So like this rail is powered with 12 volts. So if I wanted to tie the yellow and the red together and just plug it in here, I'll get my 12. But these will not work if you try to tie them together for like 1.5 volts and maybe even 3 volts. You might not even get a value on these things. It needs I think like, I don't know what the minimum voltage is, operating voltage is. So that's why I just went ahead and I put it in here, and they're all using 12 volts. And then I just plug these in, one to each power